Alrighty, let's solve some problems. So this will be going into just more examples of all of chapter 4, but mostly we'll focus on projectile problems. So problem 11. I'm going to skip around a little bit. So these are all end of chapter 4 questions. Problem 11. The position of a particle moving the xy plane is given by this formula. Calculate the position, velocity, and acceleration at t equals 2 seconds. What is the angle between the positive direction of the x-axis and a tangent line and a line tangent to the particle's path at t equals 2 seconds? So they use the unit vector notation, so I will as well. So they have something like this. So the particle's position in the x direction is given by that formula. And then the position in the y direction is given by this formula. So give me a time, I will tell you the x component and the y component. They say, okay, how about t equals 2? In which case, if you plug in numbers, you get something like 6 and negative, I think it's like 106. So it points slightly to the right and really extremely down, if down is negative. The velocity is just the derivative of position. So I could take the derivative of each of these terms with respect to time. This becomes 6t squared minus 5 in the x direction. And this becomes minus 28t cubed in the j direction. Again, evaluating this at t equals 2, I get that in that moment of time, v is positive 19, now positive 224. While the position was pointing to the right and downward, at that point, the velocity was also pointing to the right but upward. And then we continue forth with yet another derivative, evaluating at t equals 2. I get 24, negative 336. All right, so then you're seeing how give me a parametric equation, give me an equation that depends on time. I can evaluate the position, velocity, acceleration through derivatives. But now it's asking, what is the angle that the vector tangent to the path makes at t equals 2? Now the vector that is tangent to the path is the velocity vector. If this were the path as a function of time, say, and it's not for these particular ones, but just to pretend, the velocity is the vector that is just tangent to a given point. And so it is asking, given that vector, what angle is it making with the positive x-axis? So in this case, I might start by redrawing the vector so it's more obvious that it's making, perhaps that is that vector at t equals 2. And indeed, there is some angle here that it is asking us to calculate. Now with angles, triangles should always emerge in your mind. But what is the relevant triangle in this case for this angle? Well, the hypotenuse is just the magnitude of the velocity vector. That is how long the vector is and points in some diagonal direction. And then this is the y component and this is the x component of that vector. If I were to write v as vxi plus Vyj. Where actually we know Vx in this case is 19 and Vy is 224. But given this right here, we can think about this and realize that Vx equals the magnitude times cosine of the angle, or that cosine is Vx divided by the magnitude of the vector. Vx we already know is just 19. The magnitude we could calculate. So this would be 19 divided by 19 squared plus 224 squared. That thing on the right-hand side is just a number. You could take, with your calculator, the inverse cosine of that number to get a angle, and I get 1.486 radians. Or multiplying by 180 and dividing by pi is 85.2 degrees. Which, if you look at the velocity vector, that makes sense that it should be something close to 90. It's going horizontally over only 19, but then it's shooting up 224. So what I drew up here actually is somewhat inaccurate. I might even just redraw it. It goes over a little and then up a lot. So it might actually be something that looks like this. And that is V. And so if I stare at this, it does make sense that that angle looks like it's getting pretty close to being 90 degrees. (21) A dart is thrown horizontally with an initial speed of 10 meters per second towards some point P, the bullseye, of a dartboard. It hits actually at a point Q on the rim, vertically below P, almost 0.2 seconds later, 0.19 seconds. What is the distance between the rim and the bullseye? How far away from the dartboard is the dart released? Okay. So with these things, it's always helpful if can I draw a picture. So maybe I have some dart and I have some bullseye target here. And the idea is that the dart was thrown horizontally towards the bullseye, but it didn't quite hit the bullseye and instead hit at the rim of the bullseye below it. And that took place in 0.19 seconds. So this all took place in 0.19 seconds. And the question is asking, what is the distance between the bullseye and the rim of the bullseye? And what else did it want? How far away from the dartboard was the dart released? Okay, so it's also asking, there is some displacement both horizontally and vertically, actually, that it seems like it's asking for. So if I can draw a picture, then the next step is can I write down what I know as symbols? And if symbols have numbers, can I assign numbers to them? So in that case, the first thing to do is to lay down a coordinate system. If I'm going to give things numbers, I need to know where is positive and where is negative. You are, of course, free to lay down the coordinate system where you want it to. I'm going to put it so that the origin is at the dart's initial location, and that the positive direction is to the right and up. In that case, the dart starts. Yes, what is the displacement vector? And I'll use the column notation. The displacement vector is just x final minus x initial, and then y final minus y initial. So in this case, the x final appears to be some delta x, and then it started at the origin. So we could just call this, so instead of writing this as delta x, we could write it as, say, x final. Or we could give it its own symbol. We could just call it d. What is this distance d? And then for the dartboard, we're asking what is the height h that it fell below the bullseye. So in this case, the final position is d to the right of the origin. The initial position was the origin itself. This is just d minus 0, or d for the x component. For the y component, the final position was, now you have to make a choice. I'm going to say negative h. So I'm going to treat h like it's a positive number, and I put the minus sign because it's clearly below the origin on the vertical axis. Then that is minus the initial vertical position, which was just 0. So I will say that the displacement is positive d in the x direction and negative h in the y direction, where d and h themselves are assumed positive numbers. And the math better give us a positive number at the end. All right, what about the initial velocity? Here there was a clue where it said the dart is thrown horizontally. So it leaves my hand going perfectly horizontally before gravity has any time to make it change paths. So I would say it starts moving 10 meters per second in the horizontal direction and no meters per second in the vertical direction. It starts moving horizontally only in the x direction. Acceleration. In this case, I would say, again, there's no acceleration in the horizontal direction. And since I defined up as positive, I would say that the vertical acceleration is negative g, pointing downward. It is pulling the dart towards the ground. And as we see, the dart does start to fall towards the ground. It misses the bullseye. This acceleration vector is also two constants, 0 and negative g, which means then the kinematics equations apply. I'm going to call this the initial velocity in the x direction as well. So now it is the case where, since there is a constant acceleration in each dimension, this expression holds. And so I can write it out as vectors and see what we do and do not know. The left-hand side is that displacement. The right-hand side is the initial velocity in the x direction times time. And then there's no acceleration in the horizontal direction. So then that's it. In the vertical direction, there's no initial velocity, but there is an acceleration term. Now let's see. I know v, I know g, and I know t. Well, that is a treat. Because what I don't know is on the left-hand side of this expression. What I do know is all on the right-hand side. I don't even have to do algebra. I can just plug in numbers. So in this case, d is just the initial horizontal velocity times time, which they give. And if I plug those in, I get that this is 1.9 meters. And then negative h equals negative all of that. So that's the same thing as saying that h equals plus 1/2 gt squared. And if I plug in those numbers, I get that h is 0.177 meters. So again, since I had thrown out, and I'll highlight it to make it clear, since I had put in this negative sign manually, I expected h to be a positive number. So if I asked how has the vertical distance changed, it's not plus 0.177 meters. Since I put the minus sign here, I would say that it fell down 0.177 meters. Just so that it's obvious, I could have done it this way. Instead of negative h, I could have just said the displacement is d and some y. The final position is y. I don't know if it's positive or negative. And the initial position in the vertical direction was 0. So y minus 0 is 0. And I could have written down this as my two expressions. I would not get a different answer for d. And notice now there's only one negative sign. So what I would have gotten is d is 1.9 meters again. Y in this case would have been negative 0.177 meters. So in that case, the math naturally pops out the minus sign, the fact that it fell downward. That's another way you could have solved the problem, depending on what makes the most sense for how you like to approach these things. Problem 25. The current world record motorcycle jump is 77 meters, set by Jason Rennie. Assume that he left the takeoff ramp at 12 degrees to the horizontal and that the takeoff and landing heights are the same. Neglecting air drag, determine his takeoff speed. The idea here is there might have been some ramp that he traveled along, and there's a similar ramp at the end, so that if he were here, he would have kind of gone down, leapt into the air, and came back down on the other side. And it's saying that the jump is 77 meters, so the part that he's in the air, I would say that that is 77 meters. And the angle at which the jump occurred is 12 degrees, it said. So I guess if I look at that angle there, it would have been 12 degrees. And it's asking, what is his takeoff speed? So first things first, let's lay down a coordinate system. I might define a coordinate system like this, x and y, where I'm going to have the origin correspond to the point where he just leaves the first ramp. So then he goes up and comes back down. And the idea that if this is the origin, then this must be plus 77 meters. And the angle that he launched is 12 degrees. And then the question is, what is his initial takeoff speed? Again, speed, so we're looking for the magnitude of the velocity vector, not the vector itself. So again, what can we write down that we know? The acceleration vector is the same. The initial velocity vector, I could write this as the initial x component and the initial y component. But since I know the angle and I'm looking for the speed, I could also write it like this. And you could ask, why is that more helpful? Because if we look at the original form, these are two variables that I don't know, two different variables that I would have to figure out, compared to the way I wrote it on the right, where I know the angles. So I actually know cosine and sine, and there's only one number, the speed, that I don't know. So it reduces the number of variables I had to solve for. And then, do I know anything about displacement? I do in this case. I start at the origin and I end at 77 meters. So there's some, I'm going to call that d, because I prefer symbols. So the displacement in the horizontal direction is d minus 0, or is that plus 77 meters? For the vertical component, I can think I launch from a given height and I end back up at the same height. So whatever that height is, it's the same. The difference, therefore, is 0. There's no overall change in my vertical position from launch to landing. And I think that's it. I have a position, I have a velocity, I have an acceleration. The connection between these is the usual. So the last time I'm going to write that. So I could write that as d0 equals, and looks like I have v0 cosine theta times t, v0 sine theta times t, and then there is an acceleration in the vertical direction, but not the horizontal. I know d, I know cosine, I know g. I don't know the speed, and that's actually what I want, and I also do not know t, which is a pesky unknown in this case. Oops. So the benefit here is that I have two equations. Before, when we had just a single equation, if you had just a single equation, but you had two variables that you didn't know, you're out of luck. In that case, you would be unable to solve directly for those two variables. But in this case, now I have two equations with two unknowns, and that actually allows me to solve for both of them simultaneously or together. The idea is that you can take one equation, algebraically solve for one of the variables you don't know, and then plug that in to the other expression. That then makes that expression only be a function of one particular angle. Sorry about that. My computer decided to hiccup. So we were deciding how we were going to solve these expressions, which has two variables we don't know. But the fact that we have two different equations means that we could actually do this algebraically and get a single function that involves the one variable we want. Sometimes it actually helps to solve for the other one, which is the one you don't want, because that might be easier to do algebraically, and then use that to then plug in numbers to get the one you actually do want. So I think I will do that later. In this case, I'm going to do it the hard way. So the hard way is to try to just get the speed right away. So the way I might do that is look at this top equation. If I want the speed, I have to get rid of time. So I could take the top expression and solve it for time. And that would be something that looks like this. If I just solve the top one for time. And now the idea is that I plug that in to the second expression. So then that was 0 equals v0 sine of t, but instead of t, I write that as d v0 cosine minus 1/2 g t squared, but instead of t, 1/2 v0 cosine all squared. Yikes. So let us try to see if we can simplify this. At least in the first term, there's a v0 in the top and the bottom. I could cancel those out. Sine divided by cosine is just tangent, so I could write that as just... So then this first term just becomes d times tangent of theta. Okay, it's not terrible. But unfortunately, notice that there's nothing really to simplify with the right hand term. So I will just try to, well, I'll lump everything that I want and everything I don't want separately. So I ultimately want the speed. And then everything else that's left over, there's a g, there's a d squared, there's a 2. It looks like there's a cosine squared of theta. So in the parentheses, I've kind of lumped everything that's not the speed, and then there's that 1 over speed squared, since everything is being squared. So then I have some expression equal to 0. And notice here, I know d, I know theta, I know d, I know g, I know cosine. The only thing I don't know is velocity, which I can now solve for. Which itself is a chore, but doable. I will skip to the answer and let you pause this and convince yourself that you can do the algebra and get the same answer. So I get something that looks like this, I think. Using the fact, essentially, I undo the tangent and write it again as sine divided by cosine, and then one of the cosines gets canceled from the other term once you go through the algebra. Now I could look at this and ask, do the units make sense? G has, so 2 sine cosine, the denominator doesn't have a unit, so I really only have to look at the unit on the top. So the unit of square root of g delta x, sorry, delta x was not the symbol I've been using. I've been using d. Apologies. So the only things that have units are g and d, so that whole thing in the square root better have units of meters per second. G is meters per second squared. D is meters, all in the square root. That is the same thing as the square root of meter per second all squared. That is indeed meters per second. So the units work out. So that's good. Then if I plug this in, I get something like 43.07 meters per second. Really, there was a sleight of hand here as well. For the speed, when I took the square root, I should have written this actually as plus or minus what is underneath the square root. But in this case, given my coordinate system, it's the positive answer that makes sense. The negative answer actually is what corresponds to how fast the person is moving when they get to the other side of the ramp. So you could use the other kinematics equation, if you wanted to, that they leave this point with a speed of 43.07 meters per second, pointing, more vertical than, and then when they get back over here, their speed now is pointing to the right still, but down. And actually you can calculate, and you would find that the speed when just right when they land is negative 43.07 meters per second. So you might say that's interesting and seems kind of symmetrical. And you're exactly right. So now let's jump back to question 5. So question 5, the idea is that there are 3 examples here. Put this up. And the idea is that a projectile is launched. In these 3 cases, it's always launched from the same height. But in these 3 cases, the ending height is different for all 3. For the first one, it lands lower than it started. For the second one, it lands at the same height it started. In this case, it lands at a height higher than when it started. And it asks you, these projectiles are launched with identical speeds and angles. The projectiles do not land in the same terrain, however, rank according to the final speed of the projectile just before they land. So I was asking, what can we say about the speeds at the points right where it lands back onto the ground? If they are all launched with the same speed and they're all launched at the same angle. So we have seen you might ask, how can we do this without any numbers? But we have seen two examples, I think, at this point already, of that there's a symmetry to these projectile motion problems. And if you watch the optional part of the last lecture, I talked about how the path of the projectile is a parabola. Y is written as some number x squared plus some number x, etc. So it draws out a parabolic shape where it rises to some maximum height and then falls back down. A parabola is a symmetric object. So what goes on to the left of the height, or the maximum height, is completely and perfectly mirrored by what's happening on the right. So if I look at, say, this point right here and ask what is its velocity, it might have some velocity that looks like it has a positive velocity in the horizontal direction and a positive vertical velocity. Here, the velocity has turned around because now the particle is falling back down to the ground. And if they are perfectly symmetric about the center, so this is the same amount as this, so there are symmetric mirrored points, they both have the same horizontal velocity. And that actually has nothing to do with symmetry. That's just the fact that there's no acceleration in the horizontal direction. So the horizontal velocity is not changing. But their vertical velocities are perfectly mirrored from one another. One is going up. If one is going up with a vertical velocity of 1 meter per second, the other point is going down with a vertical velocity of 1 meter per second. And this is true for any 2 points that are symmetrically mirrored about the center. And I think, I suggested you could try doing that in the previous problem, that the launch velocity, the launch speed we calculated was the same as what the speed was on the other side. If you wanted to look at the components, they both would have had the same horizontal velocity, but one would have had a positive vertical velocity. The other one would have had a negative vertical velocity. That negative vertical velocity would have had the same magnitude, just pointing the opposite direction. So in this case, we can look and answer this question by symmetry. If I use the black dots to represent the symmetric points, particle 1, the symmetric point is kind of over here, which would have been kind of where you would get if this trajectory had not, if there was no wall or floor in the way. Another point is this red point is symmetric with this red point. So the speed at which the projectile was launched is the same speed at this red point by symmetry. But notice in the case of particle 1, it has an additional distance it can then fall. It has additional time that gravity can continue to accelerate the vertical velocity. And so as a result, particle 1 is moving pretty fast. Compare that with particle 2, where by symmetry, the launch speed is the same as the landing speed. As opposed to particle 3, where the points of symmetry are the 2 black dots that I drew, but the launch speed is over here, which is then kind of mirrored over here. So it goes up, rises up, loses all of its vertical velocity, and then starts to reclaim some of it. But since it hasn't made it all the way to this point, we know it has not reclaimed all of its vertical velocity, and so therefore the velocity at landing for particle 3, it must be less than the velocity it was launched at. So in this case, the answer is just the speed at landing for 1 is greater than 2 is greater than 3. Symmetry can be incredibly powerful in physics if you can employ it. Usually it's sometimes the only way usually sometimes. Sometimes it is the only way to solve particular problems. And usually it is the most effective way to solve problems. That's what I meant. Let's take a look at question number 9. So there are 3 footballs that are launched. Looks like they're kicked from the ground, no air resistance. They all reach the same maximum height, but they clearly have quite different trajectories. And the question is, rank these according to their initial vertical velocity, the time of the flight, the initial horizontal component, and the initial speed. So I like problems like this because it looks quantitative and mathy, but it really forces you to think about the concepts that are involved, not just, where can I go plug in numbers. So they are all kicked with some speed, and the speeds are different, potentially, it says. They all reach the same maximum height and then fall back down towards the ground. And they clearly appear to be launched at different angles as well. So, what does that mean? Really, what this amounts to is you can try to reason out what some of the answers might be, and then maybe the equations, even though you don't have numbers, you can always interpret the equations and see what they suggest about how particular variables are related to other variables. So for example, I claim we can already say something about the initial horizontal velocities. So I'll call it VOX. For projectiles, the only acceleration they are feeling is in the vertical direction. So like we've seen countless times now, the vertical velocities change, the horizontal velocities do not. So we might say something about the initial horizontal velocities in this case, where it looks like the green curve is covering a lot more distance than the red curve, which is covering a lot more distance than the black curve. So you might think that that is saying something about their horizontal velocities. But the tricky part is that we don't know whether or not they spend the same or different amounts of time in the air. So for example, I could write for the black curve, that's some distance d. For the red curve, it covers some distance, we'll say it r. And then for the green curve, it's covering some distance s, where clearly s is greater than r is greater than d. But what is the one-dimensional relationships again? D is simply just the initial velocity in the x direction for, I guess, the black football times how much time the black football is in the air. The red football, that distance that it covers is the initial x position for the red football times the amount of time the red football is in the air. And then similarly for the green ball, it looks the same. But we don't know how these times compare. Are they the same? Are they different? And we don't know how these and we want to say something about the velocities. Though we do have a relationship for d, r, and s. We know d is less than r is less than s. So we could say something about the times. That inequality might allow us to say something about the initial velocities. All right, well, that was a good try. The fact that they all reach the same maximum height is interesting. That suggests we might be able to calculate something. We also now have this variable t, where these represent the total time in the air. So maybe let's start, let's see, can we do the total time in the air? Can we say anything about that? So again, this is again solving the projectile problems, where we can ask ourselves, and in this case, we're actually just looking in the vertical direction. You know, the time in the air is the amount of time it takes for the ball to go up and then come back down to my hand. It might be moving in the horizontal direction while it's doing that, but the time it's in the air is determined solely by what's going on in the vertical direction. So I could look at, say, what is the vertical displacement in terms across the entire trajectory, and that's equal to the initial y velocity times t, the total time in the air, minus 1/2 gt squared. Again, this is assuming that up is positive, and so therefore g is negative, like I've drawn the coordinate system. Now what's nice is that this overall displacement is 0. It starts and ends at the ground. So then this becomes an expression for either, I could factor out a t. I might have done this in a previous problem. I'm getting deja vu here. Oh, we did do it. I recorded it like an hour ago. It's been a long day. So this gives us an expression for the amount of time the ball is in the air as a function of g and the initial vertical velocity. Which is unfortunate, right? So this doesn't quite help us yet, because I could get the total time in the air, either t equals 0, which is the starting point, or that thing in parentheses is 0. So I can say something about that t is 2 the initial vertical velocity divided by g. G is a constant, 2 is a constant. So this is also saying something about, you know, if you want your ball to be in the air longer, so t gets bigger, then you have to make v in the vertical direction bigger. If this goes up, this goes up. If this goes down, this goes down. Since the other numbers, the 2 and the g, are just constants, they don't change at all. This is an example of how you can interpret proportionalities of equations. In this case, I would say that t is proportional to v. If v doubles, t doubles. If v gets cut in half, t gets cut in half, and vice versa. All right, well, in this case, we still don't quite have the information we need because there are still too many unknowns. Bummer. What if we ask about, not the eraser, what about the max height? Is there a formula? Can I calculate a relationship to calculate this maximum height? Let's call it h. You know, they all reach some maximum height h. So in this case, delta y, again, is the initial y velocity times t, and I'll call it t sub m, so time to get to the max point, minus 1/2 gt squared. But now the displacement, you end at h and you begin at 0. So in this case, this is not equal to 0, but it's equal to h. So this suggests that h equals v naught y t minus 1/2 gt squared. And these are t's to get to the half points. But again, h depends on this other variable. See how complicated this can be when you don't have very limited information? Sometimes you just have to explore. Sometimes you just have to play around and see what works. I could have immediately wrote down the right steps, but then I feel like that gives the false impression that you should just automatically know what to do for some of these problems. Sometimes you have to just kind of explore and play around and see what do you know, what do you not know, and something might reveal itself. Like in this case, it depends now on this time to get to the max, which we don't know. Could we calculate that? No, actually we can. So we can think of what it means to reach the maximum height. We talked about this particular 1D problem in one of our in-class sessions. The football goes up, it reaches some maximum height, at which point it stops, and then starts falling back down. The key that what happened at the maximum height is that the vertical velocity became 0, and then it began to fall back down again. So at this maximum height, we know that the y velocity at that point is 0. Therefore, the 1D kinematic expression for the velocity in the y direction, which is just the original velocity in the y direction minus g times t. If I do this at the point that it takes to reach the maximum height, this is just 0. So I can therefore write the time it takes to get to the maximum height is v naught y over g. And this actually will end up being helpful. Also, as a side note, notice the symmetry. The time it took to get halfway to the journey, through the journey, is half the time it took to get to the end. There is a symmetry between what happened before the max point and with what happened after the max point. Now the nice thing here is that I can plug this back into this expression and get an expression for h in terms of just velocity and g. So in this case, I'll just go right to the answer. You should convince yourself as well. So if you plug in, v divided by g for t, your h becomes 1/2 v squared, the vertical velocity squared, divided by g. So that is if you wanted to think of it as a formula for the maximum height. But again, it's better, I think, to know just how you would go about deriving it rather than just memorizing a bunch of formulas. So this actually is what we needed to solve everything. So if I stare at this expression, I'll even give it a highlight. Now we finally have something where we can narrow it down to what's going on. G is the same for all 3 footballs. 2 is the same for all 3 footballs. And also the maximum height is the same for all 3 footballs. So H, 2, and G are the same for all 3 examples. That's now somewhat off the page. There it is. So if H, 2, and G are all the same for each of these 3 cases, the only other variable here is the vertical y velocity. So the vertical y velocity must also be the same for all 3 cases. So what this implies is that v sub y is the same for all. That implies, if I look at the equation that's conveniently right above it here, if v in the vertical direction is the same for all 3 and g and 2 are still the same, that means that the total time in the air is the same for all 3. And then if we scroll back up to when we looked at the initial velocity, now I'm saying all those different times, all those t's, even though I wrote them in different colors, all those t's are actually the same. But d, r, and s are not the same. There's an inequality there. Remember we said d was less than r is less than s. So since all the t's are the same, this implies then, just by staring at these equations, that v in the x direction for black is less than v in the x direction for red is less than v in the x direction for green. So the initial horizontal velocities are not the same for all three cases. There is an inequality. The green one is indeed launched with a faster or a larger horizontal velocity compared to the red one, compared to the black one. And so therefore, as a result, since their horizontal velocities are different, but their vertical velocities are the same, since speed is just the magnitude, the speeds also have a similar inequality. So the speed of the green curve is larger than the speed of the red curve. It's larger than the speed of the black curve. They're the initial speeds, that is. Oof, that was an involved problem. But good in that it kind of demonstrates that with some of the stuff you sometimes just have to play around. Problem, this is kind of like question 7, but I'm going to do it actually with numbers. So this is mine. So you have a rescue plane that is trying to drop off supplies to some people that are stranded on an island. And it's going to do so by dropping a payload at the exact right moment, such that as the payload falls to the ground, it falls on the island. The airplane is a low-flying plane at about 0.5 kilometer above the ground, or to move it into MKS, 500 meters above the ground. And the question is how far back does the plane have to release the payload so that it hits the island? If the plane is flying with an initial velocity, actually with a constant velocity of 150 kilometers per hour, which is 41.67 meters per second. And let us assume it gently releases the payload. It doesn't throw the payload towards the ground. It just kind of gently pushes the payload off the back of the airplane, for example. Once that happens, once it leaves the plane, the payload will then start to feel the acceleration due to gravity and will start to fall as a result of gravity. But the payload also has the velocity of the airplane. It still has that horizontal component as it begins to fall. That's what we saw with the air track. The ball, once it was launched into the air, still had the velocity of the cart. And so they kept the same horizontal velocity. And that's why they were able to, the ball was still able to be catched. It also explains, if it wasn't clear, why the plane has to release the payload before it passes the island. If it waits till it's right above the island and releases the payload, it's too late, because the payload is going to keep moving forward and it's going to land in the water. All right, first things first, a coordinate system. I'm going to do the coordinate system now. I'm going to put it at the island. I'm going to have positives be to the right and up again. So in this case, the plane is initially located, when it first drops the payload, it's initially located at negative d in the x direction and positive h in the y direction. And the island is located at the origin. All right, so what do we know? What do we don't know? Displacements. The payload starts at the plane, ends at the island. The final positions are both 0 for x and y, because I've put the island at the origin. Initially, the plane was located a distance negative d. In the x direction, again, I'll assume d itself is positive. So negative d because it's to the left of the origin. And then it's initially located at plus h above the origin, or above the axis in the vertical direction. So the displacement, how has the displacement changed? It's positive d, negative h. Which again, what is that saying physically? It moved a distance d to the right, and it moved a distance h down, which is the trajectory that's been drawn. What is the initial velocity of the payload? Again, by assuming that's gently pushed off the plane, we assume that it starts essentially with the velocity that the plane had. So the plane was moving horizontally, so it had no vertical initial velocity. And then it initially was moving at 150 kilometers per hour, or 46.67 meters per second. And I'll call this the initial horizontal velocity. And then acceleration, again, only in the vertical direction. And since up is positive, the acceleration points downward with negative g. The acceleration is constant. The kinematic equations apply. I won't copy it down again, but I'll just go right down to where I have symbols. So the displacement equals the initial velocity in the x direction times time, and then there's no acceleration. In the vertical direction, it's just the acceleration from gravity, so it looks something like this. We know v, we know g, we know h. We do not know d, we do not know t. But notice here, we can look at the bottom equation, and notice that the bottom equation only has one unknown. We only don't know t. So in this case, negative h equals negative 1/2 gt squared. The negatives cancel. T squared equals 2h over g, which suggests that t equals plus or minus 2h over g. Again, it is the plus sign answer that will be relevant, and that evaluates to about 10.1 seconds. Now we know t. So now I can say, okay, if d is the initial x velocity times t, now I have a value for t. I originally had a value for v. I can plug that in, and I get 420.9 meters. So again, what does that suggest? That suggests that the airplane better release the payload about 421 meters before it is passing directly over the island, so that by the time it reaches the ground, it will hit the island and not splash into the water. I was going to do 29, but it's kind of just mathy and symbol-y. That's a word I just made up. So I will skip it for now, or maybe I'll do it as an optional one at the end, depending on how long I've been recording. Yeah, we'll see. We'll see if I'm inspired. So let's do problem 91 and be done. So there's some volcano which launches a rock of debris that goes up into the air and then eventually falls down and hits the ground. And we are told that the height of the volcano is something. A height of 3.31 kilometers, or 330 meters. I'm missing a zero there, 3,330 meters. And that the bomb, the volcanic chunk, lands a distance d away, where d, I believe, is 9.4 kilometers, or 9,400 meters. We are also told what is the initial speed? It wants to know the initial speed if it was ejected at an angle of 35 degrees. So it's ejected at some angle, theta, where theta is 35 degrees. Ignore error. Also, what is the time of flight? So we want to know the initial speed. We also want to know the total time of flight. Now this is going to be another case where we're going to have two equations with two unknowns, and actually I'm going to find it easier to do the problem out of order and get t first, and then use that to go back and get v, so that we don't have equations like that horribly messy one I showed before with sine times cosine times the. But first things first, we got to throw down a coordinate system. If this is the volcano, I'm actually going to put the origin at neither the start or the end. I'll put the origin here. So it's directly below where the thing is launched. And it's at the same height as where the object lands. So it comes out, kind of falls like that. So then I know this height is a height plus h, and I know this distance is plus d. And this was launched with some angle at some initial speed that we would like to calculate. Again, you are free to put the coordinate system wherever you want. I keep making up and to the right the positive directions. And you could try to go back and do any of these problems again, but have positive point downward. And then as long as you're consistent with your acceleration, there it would be plus g instead of minus g. You get the same answer. All right, so what do we know? Acceleration, again, is easy. If up is positive, gravity points down. The initial velocity, again, I'm going to write it like this, since I know theta, and I'm solving for the speed. And then my displacement, final minus initial. I end up d away from the origin. I started at the origin in the horizontal direction. So then that's just d. For the displacement in the vertical direction, I end up at 0, but I started at h. So 0 minus h is negative h. I ultimately move, again, this is my displacement. I ultimately move to the right and down. Acceleration is constant. Kinematic equations apply. I could write this as dh equals my horizontal velocity is maintained throughout, but my vertical velocity does change because there is an acceleration. Now again, what do we know? We know d, we know h, we know theta, we know g. We do not know the speed and we do not know the time in both. So again, we have to kind of use both equations together to get a value for both t and the speed simultaneously. The problem asks for the speed first and then the time. But I think it's actually, again, I think it's simpler to solve for time first. So since I want time, I want to get rid of the other variable. So I could write that the speed is d divided by t cosine theta. I get that from the top equation. And then I plug that into the second equation. So minus h equals then d divided by t cosine theta. And that's multiplied by sine theta times t minus 1/2 gt squared. Now what makes this nice is there's a t on the top and the bottom here, so those cancel. Again, you have sine over cosine, which is tangent. And so as a result, this equation, at least to me, looks way simpler than if we try to get g first. Because now I have an expression where I know h, I know d, I know tangent, I know g. I don't know t, and it's a relatively straightforward equation to solve for t. H, d, and tangent are just constants, so this is only like 1/2 gt squared equals d tangent minus h. That's the same thing as t squared equals 2 over g d tangent minus h. T therefore is plus or minus, but again the minus will not be the relevant one, d tangent minus h. Oop. All of that. I can plug in some numbers. I get this is 25.88 seconds. And now why is that helpful? Because the expression we have up here is now fairly simple in terms of things we know, like d, theta, and now our new lovely variable, t. So then the speed, which is just d t cosine of theta. I know everything. I can plug that in. I get 443.2 meters per second. Wait. So the last one I'll do is actually one I'm not going to solve at all. So we could ask ourselves, we've been thinking about symmetry, we've been thinking about what these projectiles look like. We could ask ourselves for a particular problem, what is the maximum distance, and if I had to adjust my angle so that I achieve the maximum range in my problem. The cannonball makes it as far as possible away from the cannon. What is the ideal angle to use? And your book actually goes through calculating this, and they conclude that it's 45 degrees. Well, what I really like with simulations is that you can explore and play around with these things and kind of come up with an answer on your own. So I will put a link to this as well on Moodle. The only thing that you have to make sure is that when you get into this, you just have to make sure that there's no air resistance. Else you will reach a different conclusion. So the idea might be, if I want to see which angle makes it the farthest, I could take my cannon and I could adjust different angles. I can launch at some given speed. I won't change anything except the angle. And I'll just see if I only switch the angle around, how does my answer change? And which angle makes it the farthest? So for example, I could do 25 degrees. Launches a cannon. No, actually I hit the bullseye. I didn't even intend to do that. Now I could adjust it up to 35 degrees. Launch the cannon. Makes it a little bit farther. Also makes it higher, notice. Now I could do it at 45 degrees. Makes it some distance. Makes it some distance out here. Now let me adjust to 55 degrees. Goes up, comes back down. Did not make it as far in the x direction that time. Then if I go up to 65 degrees again, I should also get a bullseye. Yes. So notice what's going on. As you increase the angle, you're saying something about how much of your speed is going into vertical motion versus how much of it is going into horizontal motion. And when you have it essentially pointing straight up, all your initial speed of 14 meters per second, that's all essentially going into just your vertical motion. Your x component is very small. It would be, in that case, 5 14 meters per second times cosine of 85 degrees, which the cosine of 85 degrees is a very small number, where sine of 85 degrees is almost unity. Compared to if I have the trajectory very low and try to launch it, it gets farther out, but at the cost that it doesn't stay in the air as long as when I did, say, 90 degrees or 85 degrees. So there is a sweet spot, which ends up to be about 45 degrees. And maybe if you think about it, if you think of your trig functions, it's not too shocking because the cosine of 45 degrees is the same as the sine of 45 degrees. So you have some speed and you're distributing the wealth of equally to your vertical motion and your horizontal motion. So you're giving plenty to the vertical motion, which means that the object stays in the air longer. And you're giving plenty to the horizontal motion, which means that it's able to cover more distance before it hits the ground. Compared to, say, if you launch it at a very steep angle, it stays in the air for a really long time, but there's not a lot of horizontal velocity to get it anywhere. Versus if you do it at a very shallow angle, it's really careening in the horizontal direction, but you don't have that much time before it hits the ground. Now, of course, the extra credit, the mental extra credit, is how does that change if, say, I start and end at a different position? In that case, actually, 45 degrees is not the sweet spot, because you already have some height that you've gained from the fact that you're starting higher up. But that's an aside. All right, very good. And we'll do more projectile problems in class.